Hey, Jarian.
Hello, sir.
Yeah, hi.
Hi.
Okay, so currently you are the only one in this session. So if you want to ask anything, just shoot.
I haven't really watched the videos for this week.
Week 6, you mean?
Yeah, week 6.
Okay.
This is an open session, right?
Yes. Anything. If you have doubts in week 5 also, that's also okay.
Okay.
So half of the week 6 is just improvement of the algorithms that you studied in week 5.
Yes.
Yeah. So better to be clear on those algorithms while while watching week 6. So how was the experience of the quiz one?
Quiz was quite good.
Okay. So yeah, in 1 or 2 days, you should get your scores, I think.
Okay. It comes together, everything comes together, or it will be PDSA will be separate from app development and DBMS.
I think everything should come together only.
Okay.
Yeah.
Because I think for app development and DBMS, there are subjective questions also.
Okay.
That is manually evaluated.
Okay. I didn't know about that. Oh. So yeah, it could take time then for those. So generally, did you feel the questions were difficult or no, not so difficult?
Some of the questions, to answer it, I remembered what was taught in, I think, computational thinking or maths 1. I don't remember in which course it came.
Okay. So you have to use concepts from that.
Yes. For example, what was that? What edges will not appear in a certain tree?
Yeah.
And there were 5 options, 2 are correct.
Yeah.
So that type of question, I think we dealt with in either computational thinking or maths 1. Maths 1. I don't remember which course.
Okay.
Yeah, and generally it was the programming also. It was possible to put in that the list and find out what the answer was.
Yeah. So do you have access to some IDE or something?
On my system, I'm using VS Code now.
No. During your exam,
No. During the exam, no, there is nothing.
Okay.
No, I mean on paper. So I just wrote the input list on paper. And,
okay, that way you are saying.
Yes.
Yeah. Yeah, so maybe because of this quiz, like people would be taking some rest. And They may, like yourself also, starting late on week 6.
Yes, actually, I am starting late on week 6 because I cannot watch videos for 2 days. My internet is down. So
Oh,
I am just I'm trying to just download the PDF and yeah, I can't watch videos on my mobile internet.
okay.
That is just a specific case. Just letting you know.
Okay, okay. So I think Harsh was also here, then he left.
So while solving these graded and practice assignments, uh, is it advisable to try uh, uh, try it without using the code that is given in the collab?
So without copying that code, you
Yes,
mean?
yes,
So like 50% of the questions, you would not be able to copy anything from collab, not all of the times. Very few times you would be able to do that, right?
okay, yeah. Week 4, I think graded and practice week 4 or week 4. Most of them were just minor modifications to the collab this thing collab code.
Yes. Yes, they were minor modifications in the sense if you understand the logic.
Yes,
So if you understand what to change, that is also one part, and you are actually on the right track. If you understood, because all were not direct questions in week 4, those were scenario based, right?
yes, yes.
So if you understand what to change and how to plug in the code, then that's not a problem. But when you are asked so it depends what your aim is. If you are preparing if you would be preparing for interviews after some time, after a year from now, right? At that time you won't have any code reference for the algorithms.
Yes.
So that time you should be able to code. You should be confident that you would be able to write a DFS, BFS, or topological sort by yourself. DFS,
Okay.
BFS are very easy algorithms. You just need to know what data structure to use. You should
Yes.
know to write the code without recursion also.
Yeah.
So if you know that, then that's not an issue, because there are a lot of concepts in graph. If you know what concept to use, which code to copy, so that is also like that means you are on the right track. If
Okay.
you are not able to write complete code yourself, no issues. You need some more practice. That's it.
Okay.
So you are doing this course straight out of your school, or you have any other formal degree?
No, I have completed engineering. I am doing this after, I think my last education was 20 years back.
Oh,
So
okay, okay,
I'm coming back to academics after 20 years.
okay. So yeah, you should think on your based on your personal preferences and your aim down the line 2 years from now.
Yes.
Yeah.
But I'm learning these things for the first time.
Okay. So you are not a computer science graduate
No,
previously.
no.
Okay. So sometimes graph algorithms, if you try to write it yourself from starting, it may feel that it's a big thing, because this is a very typical case. Why this happens is because whenever you learn a programming language, you never learn it using graph concepts, but you use arrays and everything, right?
Yes.
So every person is very comfortable using arrays and with simple data structures. But in
Hmm.
case of graph, the confidence level is not that high. So you should actually try graph programs in this course,
Yes.
and those are not difficult to write the code once you get a hand on it.
What you mean is by using classes like stacks and queue and all that.
Yeah, those also you can use for writing stacks, especially for writing non-recursive code.
Okay.
Hey Manish.
Yeah, I have a-
Yeah. So do you have anything to discuss?
sir, one thing like how sir big O of Mn nearly equal to big O of Nq?
No, sorry.
Sir,
Can you be a bit louder?
sir, big O of Mn, how is nearly equal to big O of Nq?
N cube.
I'm audible? Yeah,
Big
yes,
O
sir.
of Mn is equal to big O of N cube, you are saying. N to the
Yeah,
power 3.
yeah,
Okay, so this I think you are asking with respect to graphs, right?
yeah. So lecture 5, sir had mentioned.
Okay. So that is the this equal to mean, it doesn't mean always equal. Big O is a upper bound. You understand that, right?
Yeah, yeah,
It will not be greater than that. It doesn't mean it will
yeah.
always be equal. Mn will always be equal to n cube. Mn will never be greater than n cube. Okay.
Mm,
Now, why
yeah.
is it that Mn will always be less than n cube? Not greater than, sorry. Mn will always be less than equal to n cube. So
Means
for
sir
that, yeah,
M
for
is
that you
always
will have
less than
to,
equal to N
yeah,
square.
yeah, for that you will have to calculate the upper bound for m square, m. What can be the
Yeah.
maximum value of m? M is the number of edges. So if I give you a graph of n vertices, what can be the maximum edges that the graph can have?
So
Self edge we
N
don't
N minus
consider as
1,
an edge. Generally,
N minus
n into
N
n,
minus 1.
n into n minus
Yes,
1 in case of directed graph.
director.
And in case of
So
undirected graph, it will be n into n minus 1
right.
by 2. But still it is order of n square,
Yeah,
both.
yes. Good.
Okay.
Mm,
So m can be replaced by n square for upper bound.
yeah.
So if you try to understand it in terms of upper bound, you will get this. Got it?
Yeah, yes, good. Yeah.
Okay. So yeah, we were George and I were discussing like about the quiz. Yeah, what's your opinion? How was the quiz?
Mm, so for me, it was like moderate, sir. Like neither no hard, no easy. Some question I have guessed, but what I have I was able to do. Some like
So
two, three questions. I guessed.
okay. So did you find any question that you think was not solvable using the concepts taught in the lectures?
Mm, for me, like I think I was not practice as much that required.
Okay.
The concept, yeah. It was
Okay.
maybe I can say it was my fault. Or I can.
Okay. Okay. Yeah, no issues. That happens sometimes.
Mm.
Hey Harsh.
Good evening, sir.
Yeah. So how was your experience with the quiz?
It was fine, sir. Actually, the quiz one was a little easier. I didn't expect it to be easier. In terms of the concept they taught us,
Okay.
uh, and I had few doubts, sir, regarding the week two concepts of complexity, calculating
Yeah.
complexity.
Yeah. Go ahead.
The problem I faced was I was little confused. So I wanted to know the worst case scenario is the upper bound, the best case scenario is the lower bound. That means is that the concept?
Okay. Yeah, we can say that.
All right. No, I was confused with that part, and the problem was how do you actually calculate the limits? I mean, how do you calculate the complexity of it? Like, because the sir took two examples. I think one was recursion and one was normal if loop. I mean, for loop. Uh, So if it's something like BFS and all, how do you calculate complexity for that?
Complexity for BFS, you are saying?
Yeah, I mean any program which is like usually few three for loops, it's considered to be n cube, something like
Okay.
that. So is there any
So
yeah,
yeah, is there any? Go ahead, go ahead.
is there any simple way to calculate the complexity in a program?
I would say no, because it is very input dependent, right?
Okay.
So
Yeah.
there are some algorithms for which I can just give you algorithm where, for example, you have an array of size n, and you have to find the sum of all the numbers, right? So this is also algorithm to find the sum,
Okay.
a simple algorithm. What will be the complexity of this?
It'll be in
Order
uh,
n. Worst
yeah,
case, order n. Average case,
worst case order n. Average case is I think log n.
no. Average case also order n, and best case also order n. You cannot
Yeah.
calculate sum of n numbers without seeing those n numbers.
Yeah,
There's
I
no
know.
way.
Yeah.
You got it?
Yes, sir.
If you want to calculate sum of n numbers, you have to see all n numbers.
Yes.
But you know about a lot of algorithms where worst case is different, average case is different.
Yes.
Okay.
Yes. So,
So
like you said, sir, in this case, the worst case and the best case is the same. So, is this called the other one, the theta? I forgot the name of that. There was a limit bound, I think. Upper bound, lower bound, and there was one more.
yeah, exact.
Okay.
We can say that for every algorithm we have to calculate all the these bounds differently. It is
Yeah, I got the name. It's tight bound. Is this the
it is
tight
tight
bound
bound.
case?
Tight bound.
Okay, right.
Yeah. So this won't this doesn't mean that you don't have a formula to calculate best first, and this is very much input dependent and scenario dependent. What scenario you are solving through which algorithm. So
Okay.
for another example, I will give you just now. I'm giving you simple examples, very simple examples to understand this concept. For example, I give you array of size n, I give you one number to search in that array.
Hmm.
Okay, and I give
Yeah.
you the algorithm also, that is linear search. You don't have to do binary search, just a simple linear search.
Yeah.
So what will be the best case?
Best case will be like it'll be the first element, and the worst case will be it's always the last element.
Worst case is that you don't have the element at all,
Yeah, I'm sorry. Yeah,
or
do not the
or
element.
the last element. It's
Yeah.
same thing. Okay, so you have to think based on the problem and the algorithm. For a binary search, the worst case is best case is you find the element
In the
that
middle.
is at the middle.
Yeah.
Got it?
Yes, sir.
Yeah. So for not all the algorithms will have different worst, best, and average cases. So you have to see the problem, then whatever the problem is, and based on the inputs, you will have to find what the best average cases are. And for a lot of algorithms, it's not very easy to calculate average case. It's mathematically complex task.
Yeah.
And you would have observed that some amortized analysis or some other analysis, sir may have not discussed completely for a few algorithms.
Yes, yes.
So this happens. So don't get discouraged if you are not able to calculate average case for some algorithms. But you should know. So generally, what sir has also told, that we are always interested in the upper bound, most of the cases.
Hmm.
That this will not take more than this time in any case. Upper bound means this is the upper bound. This will not take more than this much time in any input condition.
Yes,
Got
sir.
it?
So in calculating the worst case, the only possible way is what Madhavan sir told in the lecture, or is there any other ways as well? Because he told to unwind everything and calculate that way.
There could be other ways, like this. It's very vast field. Yeah, but that is, I think it would be, if there is any other way, it would just be a variation of that. Or it is
Okay.
actually a concept, unbinding. It's not a simple procedure that you can apply. I give you three statements, you can apply to any problem. So
Okay.
if that is a concept, then that encompasses a lot of things. Okay, so in itself, it becomes a big theory, unbinding everything.
Right.
Just this statement.
Okay, sir.
Yeah. So so you don't have any doubts in later weeks?
No, sir. I'm doing the week 4. I didn't understand it quite well. I didn't end moment. PFS, DFS, I'm doing right now. Then I'll move on to the week 5.
Okay. 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 So let's discuss BFS, DFS then. And there are not, if there are no questions from Manish and George, let's discuss that. Use our time. What do
Yes,
you
sir.
understand by that? Yeah, just a second. Manish, you're saying something? Hello. Your Manish, your voice is you're not audible actually. There's a lot of disturbance. Can you guys hear Manish?
Now it's okay, sir.
Yeah, it's okay now. Just be a bit louder. That's it.
Okay.
Yeah.
Sir, I have doubt in minimum separator lemma. So,
Okay.
to measure correctness of Prim's algorithm and Kruskal's algorithm on that one.
Okay. Just a second. Let me open this. Yeah. What are your doubts in that?
So I'm not getting it, like how the correctness of the algorithm is measured through the minimum separator lemma. I'm not getting the concept of that.
So this is for a Kruskal's algorithm, right?
Yeah. Like we have component that I'm not getting it actually.
Just a second. Okay. So firstly, about Kruskal's algorithm. Okay.
Yeah.
So
Yes, sir.
let's start with why do you think it's not correct? From there, we will know how to prove that it's correct. What things will encompass in proving the correctness?
So like in Kruskal's, we choose the minimum as it shouldn't let be connected to that as. We took minimum, then after another minimum as like this.
Yes. So there's a possibility that a minimum edge could be left, and
Hmm.
without that, you can create a minimum spanning tree, right?
Yeah, yes, sir.
So this is what the counter argument could be,
Hmm.
that Kruskal's algorithm is not correct. But
Hmm.
what actually we do in Kruskal's algorithm? So everything we consider them as a set in itself, uh, a minimum spanning tree in itself. Every set is a minimum spanning tree in itself. We start with every node as its every node as the set, single node as its set. Got it? You remember this or not?
Okay.
How do we start Kruskal's
Not
algorithm?
we get the weight of the minimum edge and that we append in
We
the
sort it. We sort it
yeah.
that we got. But how do we calculate that? Whenever we are adding, before that we calculate if the resulting spanning tree or resulting graph does not have a cycle. You have to check that, right?
Yeah, yes, sir.
Before adding the minimum edge from the remaining edges, you have to check
Hmm.
if the resulting graph
Yeah,
has a
the two
cycle or
vertex
not.
must not be included previously.
Not both. uh,
Hmm.
yeah, you can say both. Okay.
Yeah.
Yeah. So how do you test that?
Hmm. I'm not sure, sir. I'm not.
Okay. So the implementation is part is different, and this is different. So there we check it by having treating every node as a component initially, right? Every node is treated as a component in itself. Then whenever it connects to something through minimum age, we add that edge to the component. Okay. And we say that this is one component, this is the others are different components. Now whenever we are adding an edge, what we are doing is we are trying to connect two components.
Yeah.
Right.
Okay.
So what does this minimum separator lemma says? That whenever the edges in tree edges partition vertices into connected components, initially each vertex is a separate component. That I have already explained. Now the next thing is E forms a cycle. Yeah, that is also we discussed. Since we are scanning. Yeah. So what until now what we have discussed is that whatever components we have, in that component there are few vertices, right? Every component has few vertices. So all the vertices in those component, we create a minimum spanning tree for all the sub minimum spanning tree for all those vertices in that set, right? By choosing the minimum edges, those are added into tree edge.
And sir, if they are from the same component, then that will form cycle.
No, we have not created cycle anywhere. We will discard that edge. But what we are doing in this is so you are just thinking that we are trying, we are connecting one vertex at a time to minimum spanning tree. Do you think that in Kruskal, are we doing that?
No, sir. We add edge.
We don't. It's not necessary that we do that, right? So just a second. Let me share my screen. Okay. So can you see this?
Yes, sir.
Okay. So in this, we are at some step. We are at a step where we have chosen 4 tree edges, 6, 10, the red ones, 6, 10, and 5, 10. Okay. So what one component is 0, 1, 2, and another component is 4, 5, 6, right?
Yeah. Yes, sir.
And there's another component like 3. 3 is the third component. If there was any other node that was not included, that would be another component. So here in this graph, there are 3 components. Okay. Now the next step is you find the minimum edge to connect 2 components.
Okay.
So what the minimum separator lemma says, that if you connect, yeah, see the third point. Before that, whatever is written, we have seen that. So there are 2 components, U and W. Okay, and we are trying to connect these 2 components through edge E. E is the minimum edge. In our previous example, the minimum edge was 20. This one.
Yeah.
Okay.
Yeah. Okay.
So what we are saying is that if there is some other minimum spanning tree that is less than the cost of which is less than the cost of the one that we calculated by adding 20, the edge weight 20. Okay. Then it's not possible if 20 is the minimum edge. The minimum spanning tree that connects U and V should include the minimum edge, that is 20. If there is some other edge that is connecting component U and V, suppose there was an edge from here, suppose there was an edge from 1 to 6. right? And the weight for that was 30. So what minimum separator lemma is saying, that it is not possible to connect component 0, 1, 2 to the component 4, 5, 6 with an edge that is not the minimum edge.
Okay.
You got this? This is the
Yes, I
proof.
get it.
Okay. Yeah. So this is very simple. Don't complicate it based on the mathematical statements.
Yeah, much clear, sir. Thank you.
Yeah. Yeah. Any other doubts? Manish, Harsh, Kumar, George. Okay. So Harsh, let's go ahead with till then. If anybody has any doubts, please raise your hand. So Harsh, let's see what BFS and DFS is.
Yes,
What
sir.
have you understood till now? In very simple words. I don't want the
Um,
algorithm.
Basically, one is used to search in one is used to search the best minimum way possible.
Just talk about traversing. Let's understand through this through concept that you want to just print all the nodes of a graph.
Okay, sir.
Okay, through breadth first search and through depth first search. What is the difference between these two?
Sir,
Just
I don't
visualize
know.
it in
Can
your mind. Then if you visualize this once, and if it is clear to you, then you will
I'm a
always
little confused with it. I'm not very sure. Is it okay if you can explain, sir?
okay. So I will just help you how to visualize this so that
Yes, sir.
yeah, you know the idea how to learn things so that you can use them in applications. Okay.
Okay.
So breadth first search. So in breadth first search, what we do is if you consider a graph as levels. Okay.
Yes.
So just a second. Let me share my screen. Okay. Can you see the whiteboard?
Yes, sir. I can.
Okay. Suppose this is the graph. This don't consider this as a tree. Let me draw it completely. Okay.
Yes, sir.
Yeah. So now consider this as in terms of levels. So this is at level 1, the top node. Okay. Now
Yes.
in breadth first search, when you start searching, how can I get the pencil back? This I was facing in last time also. Okay, got it. So let's start with node 1. Okay. So whenever you do
Okay.
breadth first search, what you will do is after if you start from node number 1, in breadth first search, you will always scan all the nodes connected to 1 first. So what will be the order of scanning? One example would be you will scan 1, then what are the nodes connected to 1?
2, 3, 4.
2, 3, 4. Then you will scan 2, 3, 4. Okay.
Yes.
Then you can scan any node that is connected to the second level. So what are the
Okay.
nodes connected to 2?
5
2 and
1.
3? Yeah. 5, 6, and 7. You can scan these in any order in the third level.
Okay.
Okay. There's no fixed order. But this order, the order, this way order will remain same. This way, there's no order, fixed order in BFS.
Okay, got it.
Okay. Now, after this, what will be the order? After 5, 6, 7. What will you scan? 8.
8. Yeah.
Yeah. Suppose it was connected like this. What would have been your BFS scanning?
There will be first level 1 will be 1, then 2, 3, 4, 8.
8 would be here then, in that
Yeah.
case. Got it? So this
Yes,
is,
sir.
it's very simple.
Okay.
Now, for this, same if you want to do DFS. DFS is once you have scanned some node, you will just go, once you have scanned some children, you will go on scanning its children again and again, repetitively, recursively. So if you have scanned 1, then you will scan 2, suppose. You could scan
Okay.
anything here, 2, 3, or 4. But if you have
Yeah.
scanned 2, you will go to 5 definitely, because there is only one child of 2. So
Okay.
this is one sequence, 1, 2, 5. After 5, you can either scan 3 or 8.
3 or 8. Yeah.
Yeah, whatever you like. Suppose we scan 3. We are considering only the increasing order, in increasing order numbers. So that there is only one sequence just now.
Okay.
But it's not necessary. After 3, what will you scan? 6.
6,
Okay. After that, 7.
7.
Okay.
Yeah.
So this way you will go on.
4.
This will be the BFS sequence. What can be the other BFN sequence where we don't want the smallest number to be scanned next? It could be 1. It could be next.
1,
Could be 3.
3. Yeah. It
Yeah.
could be
Then
6.
5. Then 5 also could be there.
You told the smallest, not the smallest, so it's 6, right?
Not necessary. It could be 5. It could be 6 also. You want 6?
Okay.
Okay. That is also
Okay.
right. That is also
Yeah.
right.
7, then again 4,
Yeah.
8.
7, 4, 8,
8, 5.
5,
5, 2.
2. And suppose there is one more node here, 9. It would also be scanned.
Okay.
So you have to, when the graph is not connected, you have to scan all the nodes, all the remaining nodes.
Okay.
So there is one question related to this in one of your assignments, where if you just start with one node and if you go on doing DFS for only the connected nodes, that won't scan the complete graph because there can be disconnected components in the graph.
Yes, sir.
So got it?
Yeah, sir.
So
Got it.
yeah, so now if you go on with this concept and if you think that which will give you the shortest path from 1 to 8, if you are trying to
DFS.
calculate, DFS would be better or BFS would be better?
I think shortest part will be DFS, I think, because we can.
See, I
Not
will
sure, sir.
explain you very simply. It
Yeah.
will be BFS because
Okay.
there are a lot of ways to go to 8 from 1, right?
Hmm.
In BFS, you will go through either you will go scan 1, then 2, then 3, then 4, or 1, 3, 4, 2, whatever. But
Hmm.
what I have said is that levels will be fixed in this order.
Yeah.
So if you track the number of levels, this is level number 1, this is 1, this is 2, and this is 3. So
3.
whatever path you take in BFS, you will always reach in how many levels? And if you
3
just count the
levels.
levels, okay,
Yeah.
you got it? So the BFS will give you the shortest path, not DFS. In DFS, you can from 1 to 8, how many steps did you go? You don't have a
Uh,
definite thing to count here.
right.
From year to year also, you would have gone after 8 steps, but you have something
Yeah.
that you can count. That doesn't change the levels.
Yes.
You got the difference now.
Yes, sir. I got.
Here also you are taking the number of steps could be same. You are visiting 8 last, but you don't have something that you can rely on to count, to know the shortest path.
Yes, sir.
So this is the basic difference. Try to visualize things in this manner.
Okay.
Yeah. So how are others finding the weeks later than 4 week 4, week 5, week 6 compared to the previous weeks? Manish, George.
Yes, sir. It's like more time consuming, also getting little bit hard.
Getting a little bit hard.
Yeah.
Yeah, but this is what is these things are actually used a lot in real world scenarios. If you remember, there is a question of finding the level of connection. Anybody remembers that?
Mm, yes, sir. There was a question, I think.
Yeah.
In
So
the quiz or
in the programming, in our weekly
okay,
assignments.
GRPA.
Yeah. You guys remember
Yes,
that?
yes, 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 yes.
So anybody has used LinkedIn before this?
Yes.
So there you would have observed, George, that you
Degrees
get
of
to know
separation.
yeah, so there you get to know the how you are connected to somebody, second level of connection or first level of connection, right?
Huh.
You would have seen that. So that is a practical real world problem. That question is actually exactly similar.
Okay.
So you the difference is LinkedIn would be having a graph of millions of nodes. The number of users it has on LinkedIn, right?
Yes, yes.
And for learning purposes, the graphs, the inputs that we have given, the test cases, those are not that big, but the concept remains same.
Okay. But even LinkedIn will be representing these graphs using similar data structures, or they will be using something else.
So it's not just that simple. You cannot represent everything in real world scenarios into memory. If you are aware of RAM and hard disk storage,
Yes,
so
yes.
primary and secondary storage generally it is called. So everything, if it doesn't fit in RAM, then and you have to store it permanently. It's not input and output kind of thing. So the on disk data structures are also used for that. So you have to you have to finalize on a format how to store every node on the disk. and you have to optimize everything. You just don't, it's not just about optimizing. In our case, we have everything in RAM. It's not just about optimizing the number of operations. So if you want, if there's a better algorithm, and if there is some algorithm that may take number of steps are more, but but the reads from hard disk are less, then that would be considered, because reading from hard disk is a very costly operation compared to reading from RAM, right? So there are a lot of things that needs to be considered, but the basic concept would be same. You have you the problem solving skills that you will develop learning these algorithms, that will help everywhere.
Okay. Sir, I was able to understand the code for BFS, DFS, and topological sorting and all that.
Yeah.
But while revising for
Hello?
the exam,
George, sorry, sorry, George, there's a problem at your side in connection, I think.
I found it little confusing to.
Hello?
Hello?
Yeah, so your
So
voice
is it
is
better now?
breaking. Yeah, now it's better.
Yeah, I was saying that this BFS, DFS topological sorting, it was I was able to understand the algorithm and the Python code.
Yeah.
But while revising for the quiz, I found I was a little bit confused by the quick sort code.
Okay.
The way it works. So I referred to other sources also. So
Yeah.
just the basic concept how it works.
Okay. So did you understand after that?
Little vaguely, not concretely. I'm not 100% sure. I won't be able to explain it to another person.
So have you understood, have you seen any visualization of quicksort?
Yes, I saw a few YouTube videos of the visualization where the median is selected and then you keep going down recursively.
Okay. So just ignore the part that median is selected. Assume that we are doing the partitioning only once. We just need to focus on partition. Let's understand what is partitioning first. Then we'll understand how to use that for sorting.
Okay.
So what will we do? Will you do for partitioning, and assume that the pivot that we are picking will go somewhere in the middle.
Okay.
Okay. So you are given a list of numbers. It's very simple algorithm. So you pick the pivot as the first element. Okay. Now what you need to do? You need to select all the elements those are less than that pivot.
And move it to the left.
Yeah, and you want them all in the left side.
Yes.
They may not be sorted.
Yeah.
You got it? They may not be sorted, doesn't matter, but they will be less than
less than the pivot.
Less than the pivot. So suppose this is the array. So this is 7, 8, 12, 2, 3, 6, 11, 10, 1, 2, 5. Suppose this is the list and this is selected as pivot. Okay, this 7 is selected as pivot. Now what do you want? You want all these numbers.
2, 3, 1, 6, 1, 2, 5 should be on the left side.
Yes. You just want that, right?
Yes.
Got it. So what you do is you have two Indexes, index pointers, you can say. Pointers, don't think pointers as a C pointer. Pointer is just a variable that you are using to point to some value in the array. In that sense, I am saying pointer, right? So you have two pointers.
Yes.
This is the left pointer and this is the right pointer. Now what will you do? You move this left pointer. Okay, so suppose this, so this a number 8. So this should be in the left side or right side?
Right side.
This should be in the right side. That means you have found one number that should be on the right side. Here also you have found one number that should be on the left
Left
side.
side.
Okay, so I will take I will change a bit. I will improvise in this. Okay, so suppose here, if you are here, now 9 should be in the right side of 7 or left side.
Right.
That means it is at its right position, right? Got it?
Correct.
So you move this pointer here at next node. And now 5 should be at the left side or right side?
5 should be on the left side.
Okay. So if your right pointers points to something that is less than your pivot, less than 7, that means it is not at its right position.
Yes.
Okay. That means you have found one element that should be moved to left.
Yes.
Now by your left pointer, you need to find an element that should be moved to right. So if instead of 8, if 2 was here, then you would have found another element that should be moved. But we have found 8 that is greater than 7. That means you have found an element that is not at its right position. Okay. So what will you do? You will just swap these two. 8 and 5. You swap these two, right?
Okay.
And what will you do? You are done at this position. Just move one position ahead. Or we should not say just move one position ahead. We should actually find another value that is not at its right position. After 8, what is the other value that is less than 7? That is 2. And after this position, what is the other value
Okay.
that is greater than 7? That is 12. So we will swap
12.
these. Yeah. So we will again swap these two.
Swap 12 and 2.
Yeah. Swap 12 and 2. Got it?
Okay.
Yeah. Now again, for these both pointers, left and right, you need to search those elements. Those are not at their right position. Now, next element is 2. Is it at its correct side?
2.
2 should be in the left side. It is in the left, less than 7. 3 is also on the left side, less than 7. 6 is also on the left side, less than 7, right?
Yes.
So we just keep on going in the right side to find an element that is not at its correct side, correct position. So now the next element is 11. Here also we do the same thing. We keep on searching. We go on searching, and the next element that is less than 7 is this one.
So 11 and 1 will be swapped.
11 and 1 will be swapped. And the terminating condition would be based on the values of left and R. When they meet, that means we have found the correct position of 7.
Okay.
Got it?
Yes.
Yeah. Now you have to think with which value you should swap 7. You should not swap 7 with something that is bigger than 7. Right?
So the value before that.
Yeah, either value before that. So based on till where you go by R, what is your terminating condition? Based on that, you will have to swap. There can be a lot of different terminating condition. L is less than R, L is less than equal to R, or whatever. So based on that, you will have to design your next step. Got it?
Yes.
So now what? So finally, what you will get? Whatever strategy you use, finally what you will get?
So elements to the left of 7 will be lesser than 7, elements
So
to the
here
right
it
of
will be
7
1. Here
more
it
than
will
7.
be, yeah, here it will be 1, it will be 11. And at the end, what you will do, you will swap 7 and 1. Your 7 will be here and 1 will be here. Okay, so
Yeah.
7 is at its right position. That means you have to sort now these two parts of array. Now there are
Yes.
two yeah. Now there are
Yeah.
two parts of the array that you need to sort. This is second part and this is first part. Okay.
Yes. Yeah. Now I understood the remaining. I think recursively
Yeah,
you
now
keep splitting
recursively
it
you will do. But what
and
is the
sorting.
advantage that you got here? What is the number of elements here? 1, 2, 3, 4, 5, 6. And what is the number of elements here? 5.
5,
And initially, how many elements were there? 12. So you had to compare 7 with 12 elements, 11 elements actually, right?
Huh. Yes.
Now, if you want to position 1 at its correct position in this array, now just tell me all of this elements, these 6 elements, okay? What will be their correct position in the sorted array? This will be any position among this only, because these are less than 7. It cannot go in any place right of 7. Can they go?
No, it can't.
It can't go. That means you have reduced your problem size. Now the comparisons can't be more than 6. Okay, in this array. So to sort this array, the size of n is reduced to 6, and to sort this array, the size of n is reduced to 5.
5. Okay.
Got it? This way you keep on reducing the size.
Yes.
So this is the advantage you get. If you, so initially the algorithms that you have studied, insertion sort, right?
Those worst case are n square.
N square. So now even if you, after dividing this, you just apply insertion sort, don't do anything else. Don't go recursively for quick sort. Just apply insertion sort here. So how many comparisons will be required in the worst case? 6 square. Okay.
Yes.
And plus 11 that we have already done. Right? And plus
Yes.
5 square for this side. Right? So
yeah,
for big numbers,
yeah,
big numbers, you will observe that this will be much less than 12 square. Just you calculate and you check for other examples also. You will observe that this is always less.
Yes.
Got it?
Yes.
We will further reduce this, the size of the problems here. But just to explain, I have assumed that we don't want to reduce further. Got it?
Yes, sir. So the best time to use insertion sort is when you already have a almost fully sorted list and you just want to make maybe 1 or 2 corrections in that.
No, that would be the worst case depending on your choice of pivot. In the algorithm that
insertion, I'm talking about insertion sort.
Yes, it would be best.
So if you have 1, 2, 3, 4, 5, 6, 8, 7, 9, 10, then insertion sort will be the best.
Okay. So has it ever came to your mind that what do we do in insertion sort? So generally what happens is this is the part of the array that is already sorted. And the next element we insert in it, right?
Yes, yes.
This is what we do, correct?
Yes.
So has it ever came to your mind after reading binary search that if we use binary search, we can search the position for this element E in this sorted array S. This is sub array sorted. You can find the position of E in this S in log of size of S. Suppose the size of S is S only. So log of S time you can find the position of E, right?
Yes.
So this way you can improve the complexity of insertion sort.
Okay.
And it can become n log n, right? Or no?
Yes. Yes, yes.
No.
It can become.
Think of it more. No, there is a problem in this. In array-based implementation, there is a problem in this. Suppose you find the position of E is this. correct position is this. Okay.
Huh.
How will you move this E to here? You cannot swap these two elements. Then the array will become unsorted. Suppose this is the sorted
Okay.
array 2, 7, 9, 12. This part is already sorted till here, and you have to insert 6 and 10. So first to insert 6 will be inserted at this position, right?
Yes.
You cannot swap 6 with 7, neither you can swap 6 with 9. You can search for position of 6 using binary search in log n time. Okay, but you cannot insert it there. To insert it there, you have to move all the elements right to the position of 6, one step right. Correct. Suppose in place of 6 it would be 1. What you will have to
Yes.
do? You will have to move 12 here, then 9 here, then 7 here, then 2 here, and then you will write 1 here. Got it?
Okay. Yes.
So for
This is the
swapping,
problem of the array-based implementation.
yes. But if you
But in a
use
linked list, it will be easy. Just you have to change
no,
the.
then there will be other problem. In linked list, you cannot do binary search. The searching will be n.
Okay.
So there is one or the other trade-off. Either searching will be log n, and swapping would take n. And in case of linked list, searching would be n. Insertion would be order 1. That's why the
Okay.
best thing that we do is we directly compare this and swap. Keep on swapping. Okay.
Okay.
So you have to develop these kind of thoughts and try to counter things like if you have studied some algorithm, try to mix and match and try to counter something. If something is taught by sir, it won't be wrong, but try to think in the way that it could be wrong. Then you will learn other things. You will learn the basics and
Okay.
total concepts of the things. Okay.
Hello, sir. It's Srinivasan here. I joined late.
No issues.
So,
Go ahead.
so we are discussing sorts, right? We're not discussing week 5 and 6.
We are discussing whatever you guys have pushed.
People are asking.
Yeah, anything.
So
If you have
sorts seems to
anything,
be
just go
a
ahead.
major topic. Okay.
Anything. Whatever you feel you have doubts in, go ahead.
No, I don't have a particular doubt in week 5. Week 6, I have not watched it fully. So I would have some because that heap and those things, I always had trouble with them. And week 4 and 5, I found it because somehow I know why I like graphs or whatever. So I found it. So I don't have any particular issues myself. I could finish the assignments also. And
Okay.
I'm not, finished meaning I could look at the assignments. I feel quite comfortable doing that. So I don't have any particular question on week 5.
You will find heaps easy.
Okay.
Very easy this time. So what sir has taught heaps is actually how actually heaps are used. Like if you read heaps in terms of trees.
Okay.
So that is not the actual implementation how heaps are actually used. Heaps are
Yes.
generally complete binary tree and they are always used in array based heaps are used.
Okay.
So sir is focused only on array based.
Okay. I'll
Because that
definitely
is the
yeah.
so that would be interesting and you won't find it difficult.
Okay.
So before this we were discussing like BFS, DFS also and majorly about the quiz. How was it? So what's your opinion?
I'm trying to recollect that the quiz was actually quite good. There was one question. I was hoping that the answer key could come, then I will know what the part was. There was this related set of questions. No, actually, I think I found it quite I do have one small issue, right?
Yeah.
Which is nothing that you can solve, right? Basically, that whenever you have a graph and then you have some questions based on it,
Okay.
right? You can't see it in the same screen. It is just because the screen is small, no?
Okay.
So
Okay.
I'll end up writing the graph myself on the paper,
Okay.
which is fine. I had time, so I did it. Then I answered the question because you can't see the graph and the question together.
Okay.
Right? So, but that is you also can't help it because the limitation is
Yeah.
that, no? Because you remember that graph that had basically quite a few elements, right? Because that itself took the full page.
Okay. So I can suggest you just one thing. That's what I can do is whatever is smaller, write that. If the question is smaller, write that on the paper. If graph is smaller, draw that on paper.
I know I should actually. That's a good idea. I didn't think.
Yeah, that's it. What I can suggest.
And otherwise, I found that quiz at a good level. The term exam in Python 1,
Yeah.
the term exam was quite difficult because particularly the last, right, all the advanced topics of the Python, they covered quite a bit.
Okay. Okay.
This was much easier. I thought this may go up from there. But compared to what I was expecting, I found it easier. But again, it depends on the marks. But there are always tricky questions, right? Right from compute CT, I have seen there is a small trick in the question. So sometimes I miss it.
Okay. I don't know about Python, but neither our team nor sir is very much like reluctant about asking tricky questions
Yes.
because that doesn't make sense.
Yeah.
Trick is not a concept,
Okay.
according to him.
Okay.
So he is not very happy with tricky questions. Just like he is very much against the questions where you just change one or two odd variables or lines in a code and ask students to correct the code.
Okay. So anyway, Cherian mentions that they have been released, so I'll check the key and then. But then for that quiz, I'm trying to recollect. I think it was a very well balanced quiz I found, and usually I do well in programming, so I should probably not be the best person to answer.
Yeah.
So we should, because typically the people who have not done programming in their life, they find some of these concepts very difficult.
Yeah. So what I will suggest you from my experience in the industry also, and so that for this subject, the main focus should not be on the scoring good in objective questions. That is just one part that you
You should
have
be
to
writing the
anyways do.
program. No?
Yeah, that you anyways have to do, right? So
Yes.
you should understand the concepts first thing, and second thing, you should be able to write a program by yourself.
Yeah.
So that is very important because this is the one of the core subjects nowadays being discussed all over in the industry.
Sir, can I ask?
Yeah, go ahead.
Sure, sir.
Sir, I had an issue regarding the heapify method.
Your doubt is related to heapify method.
Yes, sir.
Okay.
So like
So what's the doubt in that?
so like actually I didn't completely got what, like how do we do the heapify, like how do we insert the method, like sir was saying like the cost turns out to be O n. So like I didn't got that part, like sir said that you have to slice from the middle and getting the leaf nodes.
Okay, so you're talking about the better heapify.
Sorry, sir?
You're talking about the better heapify that sir has discussed.
Yes, sir, they're in a heap form. So like how do we add?
So if you are, so that can be, Priyansh, first thing, that can be performed only when you are given all the numbers in an array. If I ask you, if I give you one number at a time and ask you to create a heap, that cannot be used, right? That method you are talking about.
From the beginning, sir has said that we have to start from bottom to top.
Yeah. So what I'm saying you, I will just share the screen and tell you. See. So suppose I give you these numbers. 23, 12, 6, okay, 8. So these I give you. but I don't give you these numbers all at once. I give you first this and I ask you what is the heap. So this will be the heap, right? Then I ask you to insert 12 into this heap. Where will you insert it? Here, right? So your heap will be, this will be your heap.
Yes, sir.
Now I have not given you 6 until now. Now I give you 6. Where will you insert it?
So below 12.
No.
Okay, yeah, sorry. Yeah, we will go from left to right. Okay.
Your first, the first condition of heap is it should be a complete tree.
Yes, sir. Yes, I got that part.
You can't go to next level until you fill the previous level.
Yes, sir. Yes, sir.
So this is for this is one level. This is second level. You can't
Yes,
go
sir.
to level below this until you fill this completely. Now there can be no element in this level. So now where will 8 go?
Below 12.
Below 12. Okay. So your so your heap will look exactly same as the number, same as you got the elements. This is simple example. Now
Yes, sir.
suppose I give you another number that is 17. Where will it go?
Sir, beside 8, inside 12.
Beside it. And in the array it will go at 17, but you will have to epify. The heap
Yes.
is not correct, right?
Yes, sir. We have to replace 12 and 17.
So you will check this with its parent.
Yes, sir.
Only with its parent, nothing else. So if the parent is, so this we are talking about max heap.
Yes, sir. Max heap.
Okay. So now if the parent is smaller, then we will swap these two.
Yes, sir.
So this will become 17 and this will become 12. Now you will check this one again with its parent. Okay. Got it?
Yes, sir.
So now this is already smaller, then you have to do nothing. This is hippified. Okay. So once you place 17, this was exchanged with 12 here and 12 will come here.
Yes,
So
sir.
this is how you do epify. This is also called one type of epify.
So, sir, I understood this algorithm.
And what sir has explained you is a better hipify. So the one that we just seen this is the upper bound for this is order of n log n,
Yes,
where n
sir.
is the number of elements that you want to insert, right? What sir has told us is explained is that if you are given all the elements at once in the array, not one by one, then you can do the heapify. You can convert this array into heap in order of n time. Okay.
Okay.
So how will you do that? Suppose take some example 23, 20, 19, 16, 18, 7, 12, 11, 1. Okay. Suppose this is the heap. Let's not confuse ourselves. Suppose this is the heap. Got it?
Yes, sir.
No, we have to take an array actually. Sorry. Let's take some random array first. Just give some random numbers. Tell me.
Oh, 20,
Yeah.
35, 8,
Yeah.
10, 14, 19, 7,
Yeah.
11,
11.
20. 20 is done. 20 is done. 20, 29 then.
26. Okay.
Okay. Then 54, 30.
Okay. So this is the array. So this is not a heap. Now we want to convert this into max heap. Okay.
Yes.
So suppose this is 20, 35, 8. So this is not a heap, but this is, we can suppose this, we consider this as a tree. Same as we calculate the nodes for heap. I missed something. No, right? Consider this as a tree that we want to heapify. Now what sir has taught is, what we will do is all these leaf nodes. If you leave these leaf nodes, don't do anything with these. Okay. Don't do anything with these.
Yes, sir.
What you will do is Just now we come to second level. This level we come to. Now consider only this tree. This is also a subtree.
Yes, sir.
Do you consider this as a tree?
No, yes, sir.
So now just heapify this tree.
Okay.
Don't do anything. Just
Put
heapify
six
all
would
the
be
elements
there.
in this level. Okay. So now to heapify 10, what we'll have to do?
We will replace with 26.
Why 26? Why not 11?
Okay, yeah.
We will
can
replace
do
it
it.
with 26. You are correct. But why not 11? So for that, we'll have to just check whichever is the bigger one of its childs, we'll replace it with that if it is bigger than this.
Yes,
If it
sir.
is bigger than 10, only then we'll replace this. Correct?
Yes, sir.
Okay. So now,
So we have to check with the we have to check with the parent node as well as the child node beside it.
no, you just compare the child nodes, whichever is bigger. Just compare the parent with that. That's it.
Okay.
Okay. So what was here? 10, I think. No, what was it?
Yes, sir. 10, 10.
10. So we have exchanged these two. So now how many number of comparisons we did here? Maximum we will do only one order of the height of this tree, right?
Yes, sir.
That is one. For this level, we will not do more than one comparisons. Okay.
Yes, sir.
When we go to second level, so let's do it for all the nodes. So from 14, 54 and 30, which number will be there? 54. Right?
Yes, sir.
54 and 14 here. Okay, what was here? I removed something.
30.
30. Okay. And from here and here, what will be the number? 9, 10 and 8. Got it?
Yes, sir.
Now you have, no. We won't go to this level yet. This will be the next step. Okay. So now let's go to the next level. Now for this 35. Okay. Now 35, you will replace it with 54, not 23, right?
Yes, sir.
54 and 35. 54 and 35 here. So we are not done here. We have to compare this 35 with these two also. The bigger of these two, right? 35, we have to compare with bigger of these two. Got it?
Yes, sir.
Yeah, because what if instead of 35 initially you would have told 5 just? Let's do that. Otherwise you won't get the concept, what I'm saying. Suppose it was 5 here. So 5 will be exchanged with 54. After that, this 5 we will have to
compare
exchange
it with below tree also, 14 and 30.
Yes. So you have to go till leaves. Got it?
So then every time we have to go towards the leaf, right?
But only for the half elements you are doing. So now tell me, in a complete tree, what is the, suppose it's completely filled till leaf. This
Yes,
is the
sir.
leaf. How many elements will be here?
So where?
Suppose here are n elements. This complete tree, it is n elements. How many elements will be at the leaf node? It will always be n plus 1.
Yes, sir.
Got it? So those many number of leaf nodes are there. You got it?
Yes, sir.
So we will just leave all the leaf nodes.
Okay.
So those many comparisons you have already eliminated. Got it?
So, but if we are going, when we have compared 54 and 30, we have replaced it.
Yes.
But then again, we are comparing 30, 14 and 5. So like we have to do every time the comparison, we have to do it.
Yeah, we have to do log n comparisons only. Not more than that.
Okay. So
but that too only for, but that too for,
till the leaves.
Yeah, you have to go till the leaves. But how many times you will do those comparisons? For these n minus 1, n plus 1 number of times, you don't have to do anything at all, right?
Yes, sir.
You have to do this only for these n elements.
Okay.
And that, suppose the height of the tree is, Suppose this height of the tree, this one, for example, is 10. For the below nodes, okay, for the below nodes, from this n, how many nodes will be at the last? Something
10 plus
like n by 2, around n by 2 in the leaf node here. No. You didn't get this. What I am saying is total number of nodes in this tree is 2n plus 1.
Yes, sir.
Okay. So our actual total number of nodes is 2n plus 1. Now for n plus 1 nodes, you have done nothing. For remaining n nodes, the leaf nodes, suppose you consider only this tree, this tree. Okay. For these remaining nodes, how many nodes will be this? N by 2 around.
Yes, sir.
For these n by 2, you won't do more than one step. You won't have to do more than one. So this is the 2330. Did you perform any more than one comparisons? You
No.
won't have to, right? You got it?
Yes, sir.
So you keep going above. So the number of comparison increases, but the number of node decreases. For that you have to do. So log n comparisons, you will have to do log n comparisons only for the root in worst case. And if that is the greatest number, you don't have to do any comparison, but we are talking about worst case. Suppose here it was 0. This is the smallest number. Suppose this 20 would have been 0, right?
Yes, sir.
So to place this at its correct position in the heap, you will have to do how many comparisons?
With 54, you have to compare.
Maximum log n.
Yes, sir.
Capital N.
Worst case, yes, sir.
Worst case. For this level, how many comparisons you have to do?
-1.
-1. So you got the point now. What is reducing and what is increasing?
Yes, sir.
Okay. So when you do the math, it will come to order of n. Because when you go above, although number of comparison increases from 1 to log n. For
Yes,
this
sir.
level, it was 1, then 2, then 3 till log n. But the
Yes,
number
sir.
of nodes keep on decreasing. At the root, it is only 1. You got the point?
Yes, sir.
So that's why the complexity reduces. And when you do the math, you will get it order n.
Okay,
For
sir.
that, yeah. So that sir has already explained. This is
Sir, yes,
yeah.
sir.
Yeah. Go ahead.
Yes, I got this part now. So I had another doubt regarding the components part.
Okay.
Like sir had told that we will start merging the different components that we get after we
Which
have filled in the union form, the union.
union find?
Yes, sir. So, sir, at last, don't we have to like make it as a one tree, merge it into one tree?
So firstly, understand that union find is just extra store, some extra data structures that we are using extra storage for computing our algorithm fast. The algorithm doesn't change. Kruskal's algorithm remains same.
Yes, sir.
Okay. You don't change anything in the algorithm when you implement it using union find.
Okay.
And now what you are saying is that don't we have to? Okay. Now what was the doubt regarding components?
So we have to merge at the end, right? Like when we have divided it into components, at the end, don't we have to merge it into like getting one tree at the end?
Yes, we have to. Do you remember the members? There's a members array, members set.
Yes, sir. Yes, sir.
So that will have all the vertices. But it doesn't matter. But it doesn't matter because if you are able to create a spanning tree, that will have all the vertices. So at the end, it doesn't matter. This members matters only in the middle, in the intermediate steps. Got it?
Yes, sir.
At the end, the tree will have all the vertices. Agree or not? Otherwise, it's not a minimum spanning tree complete.
Okay, sir.
At the end, you will have all the vertices in the minimum spanning tree. So this members is only used to calculate, to speed up your operations in intermediate steps. So that by this members, you know what are the components of the component that you are merging. So you have to update the component only for those members. So there are suppose two components, U and V. So this has some nodes and this has some nodes, right?
Yes, sir.
Okay. Now you call it component U, and this is component V. Now this V has a smaller number of vertices. Okay. Now for all these vertices, only the vertices, those are in V, you will update the components and call them as U. So from
Yes,
where
sir.
you will get this information? From the members of V. Got it?
Yes, sir.
Yeah.
So like, sir, but this is a better algorithm than the Kruskal's main algorithm that we do.
That's what I'm saying. It's the same algorithm. You just have used extra data structures to implement the same algorithm, so that the operations, those were taking order n, will start taking order log n.
So like, sir, it is a more efficient algorithm. That's what I'm saying.
Yes, it is more efficient implementation.
Okay.
So if you talk about algorithm, right? If you don't talk about how to implement it, so it is either using union find or without union find. The concept is same, that you take the smallest edge, add it into the tree edges, and see if the cycle is not created, right? How to find the cycle? That is implemented in two ways. One is with using union find, other is without using union find. But the algorithm is same. At the edge, see if cycle is not there, then at the edge. Got it?
Yes, sir.
Yeah. So any more doubts? Anybody?
No, sir. I would watch the video and then for the exercise 6, and I would ask some more questions if I have. I watched some of them, but otherwise I don't have any questions. And then I also thanks Cherian mentioned that the answer key has been posted. So
Yeah.
I went and looked at things. I think I think I go with that. So the questions are quite balanced, and then I think they covered the concepts quite well. I mean, they asked about the various concepts, right? I think the entire 4 weeks, the entire part was covered. It's a good, well balanced question paper.
Yeah.
But there is one question I
for
think
everybody.
I got wrong, so I have to go figure out what I did wrong.
Okay. Okay. So if you have any doubts, tomorrow is also one session. If
Yeah,
you
we'll
guys
do
can
that, yeah.
attend that.
Yeah, I will also attend the MLF and ask them. So the MLF, I'm doing MLF. That was tricky. So somehow the math team generally they make it a bit more
Okay.
trickier than needed, I guess. Maybe.
Okay. Okay.
Thank you so much.
Yeah. Good day. Okay. So, and if there are no doubts, that we'll close the session. Manish? Okay. So good day, guys.